No sé por qué a mí no me sale lo de la webcam, no me va. Esto, a ver.
¿Le has dado al botón de abajo ahí de la cámara?
Y entonces me da configuración de la webcam. No se encuentra la webcam, por favor, de que está conectada.
Ahora deberías tener otro botón abajo para presentar tu pantalla. Es que no eras presentado. Tienes que tener 4.
Sí.
Vale, pues ya puedes presentar pantalla o aplicación, lo que quieras. Pantalla.
¿Ves mi pantalla?
Sí.
Yo sí.
Muy bien.
Perfecto.
Lo que no aparece es para mí, pero igual no está. Gonzalo, ¿está previsto que yo pueda aparecer? No. No hace falta tampoco, vamos.
Bueno, tú si quieres poner tu cámara, tú la puedes poner.
Ya, es que no me está dando permiso, no me está dando acceso.
No, tendrás que aceptar seguramente en algún sitio te pregunte permitir. Cuando entras aquí, permitir a la cámara que acceda, o sea, a Big Blue Button que acceda a tu cámara o algo así. Pero bueno.
Pues igual.
Hablas y ya está.
Claro.
Vale.
Tampoco es.
Te conocemos todos.
Te conocemos. Voy a poner una foto. A ver, esta aquí fuera.
Pepe, eres tú el chair de la sesión, por lo que intuyo.
Te introduce él.
Sí. Lo que no sé si tengo que continuar con. Luego va.
Como quieras, lo despides a él y si quieres continuar luego, puedes continuar. Si no, pues se encargarían Adrián y Alejandro, se presentan entre ellos, son de la casa. O sea, bueno,
Ya.
Alejandro es de la casa.
Alejandro, sí, Marianne también, pero luego, después de Iván va una chica, va alguien, a ver qué.
A ver, que tampoco tengo yo aquí el horario. A ver. Vale, no, después de Iván va Lupamudra, Sharma y luego Alejandro. Vale,
Claro.
yo puedo presentar hasta Alejandro, luego me tengo que ir a por los niños al colegio.
Lupamudra Sambra, ¿no? Lupamudra Sambra, que es del Indian.
Sí. Eso es.
Indian Institute of Technology.
Exactamente. Bueno, ya cuando es la hora, no sé cuánta gente hay aquí, a ver, déjame. Bueno, vamos a esperar un poquito que se vaya conectando la gente.
Bueno, me quitéis el tiempo, ¿eh?
Vale, ya están ahí ellos también en la sala. La emisión funciona en YouTube, así que nada, cuando queráis. Peínate, Iván, está guapo.
Okay, so I am very pleased to introduce Professor Iván Agullo from Louisiana State University. He has been a former member of our department here in Valencia. And before being permanent in Louisiana, he has been a postdoc in Wisconsin, Milwaukee, working with Professor Leonard Parker. Also in Penn State, working with Bayastekar. And he has enjoyed a Marie Curie fellowship in Cambridge University. Well, he's going to start the last session of our winter workshop with a talk about squeezing and entanglement in the early universe. So, Ivan, we are pleased to hear your speech. Thank you.
Thank you, Pepe. Can you hear me well?
Yeah.
So it is a wonderful pleasure to contribute to this winter workshop. As Pepe said, Valencia is my alma mater and what I like to call home. So I would like to be there, but because the current situation, I am not. But at least I can contribute with a talk. And I know that this is a very special workshop because most of us are good friends and more than colleagues, we are friends. So I was, and also there are a lot of students. So I was thinking in giving with very little technical details and a talk from which many people, in particular students, can benefit. And I came out with this title, Squeezing and Entanglement in the Early Universe. And so I hope I can entertain you for 45 minutes and hopefully you can get something out of it. This is a project which is ongoing, is work in progress, and I thought this is good for this meeting. And it's done in collaboration with a student, a PhD student, Patricia Ribes, who is from Spain, but is doing her PhD co-advised by myself in the Netherlands with Beatrice Bonga. And again, it is work in progress, so any comments you may have are more than welcome. So I will tell you today what I understand about this matter at this point of time. So let me start with a motivation. The first thing I want to do is to read the abstract because it will give you a good overview of what I want to do. So the abstract says the theory of cosmic inflation, which is a cornerstone of modern cosmology, rests or is based on a process of two-mode squeezing, which generates pairs of maximally entangled particles out of the vacuum. These particles play a pivotal role in the subsequent history of the universe. They seed the primordial density perturbations. So they are the origin of the primordial perturbations in the cosmos, which later grow because of gravity and end up forming the cosmic structures that we see today, including ourselves. And what I want to do is to provide a pedagogical summary of this subject and a critical view on an ongoing discussion about the experimental verification of the quantum origin of the cosmic structures. So let's go for it. Let me start with a bit of history. Yesterday, Leonard Parker was mentioned, and as a tribute to him and to his legacy, I want to start with the first page of his thesis, The Creation of Particles in an Expanding Universe. This was in 1966. He was a student in Harvard, and he made this outstanding discovery that initiated a whole new research avenue that today we call quantum field theory in curved spacetimes. And what Parker realized, what Parker did was to put quantum fields living on a spacetime which is not Minkowski, but has non-trivial curvature. And he did it for a case of relevance, which is our own universe. So he considered a Friedman Limit Robertson-Walker metric, which is time-dependent, characterized by a single function, the scale factor. And he considered this perhaps simple and perhaps academic situation, a situation in which the scale factor is constant in time initially, then grows, and then becomes constant in time again. And these two asymptotic regions, which are flat, are very convenient because you can use the standard tools of quantum field theory here, and compute the S matrix between things here and see what is the effect of the expansion of the universe. And what he obtained, as most of you know, probably all of you, is that this evolution can be phrased in terms of what we call today Bogoliubov transformations. In particular, the creation and annihilation operators in the initial and final region are related by a transformation of this kind. A, K for a mode of wave number k, becomes a mixture of A in and k and A in minus k dagger, with some coefficients that we call Bogoliubov coefficients. And this mathematical statement has unforeseen consequences, which is what we call the phenomenon of particle creation. That is that if you start with the vacuum at the initial time, so initially there are no particles, the in observer will say this is the vacuum, and you do time evolution and ask at the end how many out particles are. So notice that I am changing the question. Initially, no in particles. Finally, we ask how many out particles are. In the Wolf state, the answer is non-zero. Therefore, we say that the expansion of the universe spontaneously creates particles out of the vacuum. And these particles come in pairs. If you do the calculation, they come in pairs of particles with momentum k and minus k. And that is because momentum has to be conserved because of the homogeneity of the space-time. And these particles are maximally entangled. And in the modern language of quantum information, we say that the vacuum evolves to a two-mode squeeze vacuum. Again, a two-mode squeeze vacuum is just the result of the evolution, and it is made of a tower of states with even number of particles maximally entangled and moving in opposite directions. And as I advertised in the abstract, this was used in the theory of inflation, because the theory of inflation, remember, inflation is a phase of the early universe in which the space-time expands almost exponentially, and that is going to create, applying Parker's idea, this is going to create lots of pairs of particles, again, maximally entangled and moving in different directions. And as I advertised, in inflation, these particles are the primordial density perturbations that later grow because of gravitational instabilities and form the anisotropies that we see in the CMB, and later on the entire large scale structure, including cosmologists and students. And this, as you can imagine, is a completely outstanding statement. We say that the entire cosmic structure is originated from vacuum. Vacuum, which is amplified by an expansion of the universe, and later on gravity does his job and produces all what we see. So everything from nothing, all the cosmic structures out of the vacuum, the closest thing to nothing that we have in quantum mechanics. So this is an extraordinary statement. So the question that is on the table is whether we can test in observations this extraordinary claim. As you know, extraordinary claims need extraordinary evidence. So there is a debate in the literature about the role of this squeezing and quantumness of the extraordinary mechanism to originate the cosmic structures. Questions on the table are as follows. If the origin of the CMB inhomogeneities is really quantum, why cosmologists only use classical tools to analyze the CMB? Is there anything genuinely quantum in the CMB which can confirm this quantum origin or not? Some people argue that yes, the origin is quantum, but the CMB looks so classical precisely because of squeezing. And there are many references, and I apologize, I will not include all of them, but just the main ones. But the original paper is by Kiefer, Polanski, Starobinsky, etc. But not everybody agrees. And last week there was a paper by Baylock Hu and collaborators, criticizing this argument. So they say that precisely because of the squeezing, the CMB looks very classical. In contrast, a different line of thought has been raised mainly by these two authors, Jerome Martin and Centenin. This is one of their papers, but there are many, and they are really good, so I recommend you to read them. They say that the other way around, that squeezing is, is genuinely quantum. And in particular, squeezing comes together with entanglement, and therefore with quantumness. Therefore, the CMB should be very quantum, and there should be a way to observe that. So this is in tension with the other argument, and I read these two papers and others, and I had my own questions, and that was the motivation for my interest in this field. My questions are the following. First of all, I want to understand in which precise sense can we say that there is a generation of squeezing during inflation. So mathematically, let's go to details and see in which sense we say that inflation squeezes cosmological perturbations. The same for entanglement. In which sense we can say that inflation creates entanglement. And last question, this is theory. And last question is, okay, we are physicists. Let's go to data and see what data can tell us about these two questions. By the way, you are welcome to ask questions in between if any clarification is needed. If the question is long, you can wait at the end, but if it is simple, just for clarifications, please go ahead. So just for the sake of completeness, let me talk a little bit about squeezing, entanglement, and quantumness in quantum mechanics. So this is going to be very simple, and most of you know it, so I apologize if I say something trivial. So for simplicity and for concreteness, let me focus on Gaussian states, although most of things I'm going to say are true in general, but we know CMV is very Gaussian, so just data tell us that Gaussian states are a good approximation of an excellent approximation of what inflation produces. So this is enough for our purposes. Although many other people are working with the effects of non-Gaussianity in squeezing and entanglement, and that is also very interesting. But because we don't see non-Gaussianities in the CMB, I will restrict myself to Gaussian states. So let me talk about the squeezing. So remember the definition of squeezing. So if I give you two operators in quantum mechanics, I will call them a quadrature pair of operators whenever their commutation relations are just the canonical. And also, just let me normalize them with a dimension full factor in such a way that both of them have the same dimensions. For instance, dimensions of a square root of action, because h bar is here, so square root of action, each of them. This is called a quadrature pair. This is just a name. We say that a quantum state, raw, mixed, or pure, is squeezed relative to x and y whenever either the dispersion, the quantum dispersion of x or y, is below their share of the Heisenberg lower bound, of the Heisenberg principle. The Heisenberg principle tells you that the product must be larger than 1/4. So whenever either of them is smaller than 1/2, we say that the state is squeezed. Very important, the notion of squeezing requires two things, a state and a pair of operators. So you cannot tell me that a state is squeezed unless you tell me which operators are you referring to. So squeezing refers to both state and a quadrature pair. And that will be important later on. So, theorem. For all Gaussian states, every single Gaussian states, there always exist quadratures, quadrature pairs with no squeezing at all. And also quadratures with arbitrarily large squeezing. So again, if you give me a Gaussian state, I can always find a quadrature for which there is no squeezing, or even a basis of quadratures for which there is no squeezing, and another basis for which squeezing is arbitrarily high. And I want to say this because we normally associate the notion of squeezing with states, and I want to emphasize that we shouldn't do that. Because the squeezing can be arbitrarily different depending on the operators that I focus. And I'm going to prove this theorem quickly, just because of time. So the proof is the following. You can go to this book for most of the things I'm gonna say. So consider a bosonic system. I'm working with bosonic systems with n modes. n x and the corresponding conjugate momentum. Remember that a Gaussian state is completely characterized by the first and the second moments. All the other moments for a Gaussian state can be written in terms of these two moments. This is why Gaussian states are so simple. And this, this is equivalent to what happens with Gaussian functions, right? A Gaussian function only requires the mean and the variance. That's it. The mean, I'm going to call it mu. And the second moment, rather than working with the second moment, I'm going to work with the symmetrized version. This curly bracket, in fact, I forgot to add a curly bracket here, is anti-commutator. So this is just the symmetric version of the second moment. And the reason is that the anti-symmetric version is a state independent, is proportional to the commutator, and therefore doesn't know about the state. So first moment and second moments. This symmetrized version is called the covariance matrix. And example of Gaussian states is the vacuum. First moment 0, second moment identity, coherent state, which is the same covariance matrix, but the mean is different. So a coherent state is called a displaced vacuum, just because of the mean is different. A squeeze state has 0 mean, but non-trivial covariance matrix. Thermal states, they are also very simple. All of these are Gaussian states. So Gaussian states, encode a very useful family of states. So there is a theorem called Williamson Theorem that tells you that for all Gaussian states, there always exists a canonical transformation from the old variables to the new variables, for which the covariance matrix takes this diagonal form, where the eigenvalues appear in pairs. These are called the symplectic eigenvalues. And these eigenvalues must be larger or equal than 1. Equal to 1 if and only if the state is pure, and larger than 1 if the state is mixed. And that is always possible for all Gaussian states. You can do a change of variables and the covariance matrix becomes diagonal. But this diagonal contains precisely the information about the variances. This element, if you want the variance of x, each x is given by half of the corresponding symplectic eigenvalue. And the variances of p also given by half of the symplectic eigenvalue. But because in this diagonal form, they are larger than 1 or equal than 1, this tells you that in this basis, in the basis which diagonalize symplectically the covariance matrix, that there is no squeezing. The dispersions are larger than 1/2. So I just proved to you that there is always a basis for which there is no squeezing, a basis of quadratures for which there is no squeezing. Now, if I take this basis and just do this trivial scaling, I divide by alpha x and multiply by alpha p. This is a canonical transformation. The dispersion of x is going to get multiplied by 1 over alpha squared, and the dispersion of p is going to get multiplied by alpha squared. So tuning alpha, I can make the dispersion of x as small as I want, or the dispersion of p as small as I want. So this is a proof that I can make, the state as a squeeze as I want by changing the canonical variables. So I can remove the squeezing by a choice of variables, and I can make it as big as I want by another choice of variables. So therefore, we cannot simply say that a state is squeezed. You need to tell me the quadratures that you are interested in, the operators you are interested in. Why then you read many times in textbooks that some states are non-squeezed, like the vacuum or coherent states, they are not squeezed, and other states are squeezed, and they never mention any quadratures. We can see this statement in most elementary textbooks of quantum mechanics. Squeeze and non-squeeze states, and they don't mention quadratures. So what is going on? What is going on is that for simple systems, and in particular for time-independent Hamiltonians, there is always a preferred set of quadratures. For instance, for a Hamiltonian, you can always diagonalize the Hamiltonian. You go into the normal modes in which the Hamiltonian looks like this. That is always possible for quadratic Hamiltonians. And these quadratures are preferred. These are the normal modes. And that is equivalent to choose a preferred creation and annihilation operators. So you know, when there are preferred quadratures, the notion of squeezing refers to them. So implicitly, whenever we don't mention which quadratures we are using, is because there is a preferred choice. And you can, and this is what I say here, that the eigenvalues of the preferred annihilation operator, which is the ground state, the zero eigenvector, and coherent states, the non-zero eigenvectors, are precisely not squeezed for these preferred quadratures. But if there were no preferred quadratures, for instance, because the Hamiltonian is time dependent, then you need to tell me what you are going to use. So whenever we don't say it, it's because there are preferred quadratures, and if there are no, we need to specify our choice. Trivial example, the time-dependent harmonic oscillator. So you have this oscillator with a time and frequency, and the frequency I am choosing for simplicity this shape a la Parker, time independent, changes time independent. And because you know the Hamiltonian is time dependent, there is no ground state of the Hamiltonian, energy is not conserved, and there are no preferred quadratures. In this particular case, I can choose two different set of quadratures. The ones in the in region, these are you know, obtained from X and P. Remember that I need to add a dimension full factor to make them with the same dimensions. And the only dimension full factor is the mass and the frequency. So, but the frequency is time dependent, so I need to choose a time. But if I choose the initial time, I can define the in quadratures. And if I choose the final, so I can define these in quadratures and the associated annihilation operators and the associated vacuum. But I could also use the frequency at late times and define the out quadratures. And they are different than the out vacuum. And, you know, if I choose the in vacuum, this is not a squeeze for the in quadratures, but it is a squeeze for the out quadratures, and vice versa. So the notion of squeezing becomes ambiguous, and you need to tell me which quadratures you want to pay attention to. At the initial time, you can argue that the natural quadratures are the in ones. At the final time, you can argue that the natural quadratures are the final one. And this is an example where the natural notion of quadratures changes in time. And that this will be important later on. So the message I want to convey here is that there is a close relation between these two questions. Does the evolution create particles? And does the evolution generate squeezes? And the reason, let me come back, the reason is that, you know, the quadratures are associated or are related to notions of creation and annihilation variables and to vacuum state. And from here, you can get the idea that there will be generation of squeezing whenever there is generation of particles and vice versa. So this is a simple message that most of you will know, but I want to emphasize that there is a relation between generation of squeezing and generation of quanta.
Ivan, excuse me.
Yes.
There is a question on the chat.
I don't see the chat.
Okay, I can read it for you if you want. Adrià Delhomme is asking, Ivan, is there a preferred notion of quadratic?
Sorry, I cannot hear you. You need to repeat.
Ivan, is there a preferred notion of quadratures at all times? Or that notion can only be made sense of asymptotically?
Wonderful question, Adrian. Thank you. No, of course, as I will argue in a second, here we have notions of two preferred notions, which are different, because I am using the fact that the Hamiltonian is constant, is time independent during this time. At intermediate times, I will not know how to do it. For an harmonic oscillator, for a single harmonic oscillator, maybe you can use the instantaneous frequency to define quadratures at every single intermediate time. But that will not work well in quantum field theory. So the message is no. In quantum field theory, whenever it's time dependent, I don't know how to define particles or preferred quadratures. I know, but it's highly ambiguous. You can choose something, I can choose something else. There is no preferred choice. And that will be important later on. So entanglement, let me speed up a little bit. The similar argument happens for entanglement. If you give me a Gaussian state now with n modes, we can always find a basis of quadrature pairs, xi and pi, for which there is no entanglement. That is always possible. You can always find a basis for which, for any bipartition of the basis, if you if you divide it into subsets, there is no entanglement between them. Again, one can also find a basis of a different basis, a mix of the initial ones, for which there is as much as entanglement as you want. So therefore, entanglement is not associated to a state, but rather is intrinsic to all multimode Gaussian states. The entanglement of a bipartition, of course, depends on which bipartition you choose. And choosing the bipartition, you can make the entanglement as large or as small as you want. For quantumness, the same. All Gaussian states are equally quantum. We normally say that coherence are more classical than squeeze states, but as I already argue, that is not true. That depends on your basis of quadratures. That depends on where you are looking the state from. So, message of this introductory section: when there is a preferred basis of quadratures, the implicit convention is to associate the notion of squeezing and entanglement to the preferred choice. But the squeezing and entanglement are intrinsic aspects of all Gaussian states. All of them are equally quantum. Okay, let me go to the meat of the talk. Subtleties of time-dependent systems. And this is where the question of Adria appears. So the notion of vacuum and number states are not unique at intermediate times. This is precisely Adria's question. When the universe is expanding. So in Packer's example, as I told you, we can argue what the vacuum is initially, what the vacuum is finally, because we have symmetries there, flat space symmetries. But in between, we don't have any symmetries, and there are different choices, and none of them is better than other. It is ambiguous to talk about particles and vacuum in an expanding universe, except when you have symmetries in very special circumstances. Consequence, because the quadrature describing modes with wave number k, to define quadratures associated to a wave number k, I need creation and annihilation operators. This is the way you define Hermitian operators for a mode k and for a mode minus k, if you put. But if there is ambiguity in what A and A dagger are, there is ambiguity in what X and PX are. PK are. So there are no preferred quadratures for modes with wave number k and minus k. And just to tell you, to emphasize how important is this for squeezing, let me show you these formulas. Imagine you have two different choices, A dagger and A tilde I dagger tilde. Because of homogeneity and isotropy, they are related by this sort of Bogoliubov transformations. A tilde must be a combination of AK and A dagger of minus K. This is needed, this minus is needed if you want that the vacuum tilde is homogeneous and isotropic, otherwise it will not be. And of course, these coefficients must satisfy a normalization. But if you translate this relation to the quadratures that they define, the quadratures X is a mixture of the quadrature X for K and X of minus K, and P of K and P of minus K. So this ambiguity in the definition of A's and A daggers mixes K's and minus K's. So I tell you this because, you could think that, if you have these two sectors, modes K and modes minus K, you could think that the ambiguity just mixes K among themselves and minus K's among themselves without mixing them. But that is not true. The ambiguity mixes them. And therefore, it is not clear, there is no unambiguous separation between modes K and modes minus K because different choices mixes them. For the quadratures, I am speaking, for X and P, these canonical operators. The question, does a given state contain entanglement between degrees of freedom K and degrees of freedom minus K, does not have a definitive answer in an expanding universe. This question, there is entanglement between these two sectors, requires of a choice. And if there is no preferred choice, there is no preferred answer. So this is one of the main messages I want to convey. So let me just stop for a second. So one of the things I have learned is that speaking about does the universe generates a squeezing between sector K and sector minus K is as ambiguous as the question, does the universe generate particles? Different authors will provide different answers. Because there's intrinsic ambiguity in time-dependent spacetimes. So the question to me is a bit, I wouldn't say meaningless, but unimportant because requires of a choice. It's not invariant. So there are as many answers as authors in the market. Therefore, the physics, the real physics that we measure shouldn't depend on that. So this is the main message. The generation of a squeezing and entanglement in an expanding universe doesn't have a good answer. Let me now jump to inflation, not a generic expanding universe, but concrete inflation. Inflation is special because the scale factor has almost this simple functional form. The scale factor grows almost exponentially in time. This spacetime acquires more symmetries than a generic Friedman-Lemaitre-Robertson-Walker. A generic Friedman-Lemaitre-Robertson-Walker has 6 symmetries, 6 Killing vector fields, translations, and rotations. When you have this extra, this concrete functional form, a new Killing vector field appears. So you have 7 Killing vector fields, and this spacetime is a portion of de Sitter space. The Sitter space globally has 10 isometries in 4 dimensions, but the universe, during inflation is only a portion of de Sitter, and that portion has only 7 Killing vector fields. But that extra Killing vector field is important and makes the spacetime special. As I said, it has more symmetries than arbitrary FRW spacetime. These symmetries can be used to select a preferred vacuum. So if you want, I insist, you can use the extra isometry to single out a preferred set of creation and annihilation variables, define the so-called Bunch-Davies vacuum, and from them, you can define preferred quadratures. So in inflation, the ambiguity goes up if you want to use the symmetries. Of course, if you don't want, the ambiguity remains, but at least you have this option. You have a good argument to choose some preferred quadratures. And then it's quite simple. I don't show the calculation. I just tell you what it happens. That, if you give me the Bunch-Davies vacuum at initial times and you evolve it, the evolution is still the Bunch-Davies vacuum. I am thinking in the Schrödinger picture. So take initial state, evolve it. If the initial state is the Bunch-Davies vacuum, the final state is also the Bunch-Davies vacuum. Therefore, if you ask a Bunch-Davies observer if there is a squeezing in the final state or in the initial state, a Bunch-Davies observer, an observer with the Bunch-Davies quadratures, X and P, will tell you that there is no squeezing initially, there is no squeezing finally. That observer will tell you that the final state is the vacuum, exactly as the initial one. So I want to argue that if you want to use the de Sitter symmetries, there is no generation of particles during inflation, and there is no generation of squeezing or entanglement during inflation, again, with respect to these preferred quadratures. So this is an example where, where the answer depends crucially of your choice. And I want to argue that there is a reasonable choice for which there is no generation of squeezing. So no generation of squeezing or entanglement between K and minus K for Banks-Davis observers. But as I said before, and I am getting to the end of the talk, because the question itself is ambiguous, we should wonder what is the relevance of this discussion for observations, for what we measure in the CMB. In physics, every time a question is ambiguous, normally it is not really relevant for physical observations. And in my opinion, the same happens here. So first of all, what do we observe in the CMB? So we observe the field in position space. So we go to the CMB and we measure the field there and the field there and the field there in real space. So this momentum space or wave number space, this Fourier space, is a tool that we use, and from it we should extract, what we measure in position space, but we don't measure directly Fourier modes, in particular because they are unphysical, because they are everywhere in the universe, right? A plane wave is, permeates the entire cosmos, and we have access to the CMB. So what we measure is the field smeared in, average in regions of the sky. So we measure the temperature of each pixel of the CMB. This is a measure of the average value of the field in each pixel. So we measure the field here, we measure the field here, and we study correlations between the values of the field in different regions, again in real space. So we could ask if there is a squeezing between this degree of freedom. So now the degree of freedom is the field in space and the field in space. And if there is entanglement between these 2 degrees of freedom. But again, this is very different from the K and minus K things that we said before. That is gone. We don't have K and minus K here. We just have the field in real space. But so I'm going to try to answer, then reformulate the question. Is there a squeezing or entanglement between this degree of freedom, the field averaged here, and this degree of freedom? So forget about what I said before. It's an ambiguous question, not directly related to the CMB, and I want to reformulate the question in real space. To answer that question, I need to recall you that to define squeezing and entanglement, we need canonical pairs. And this is very important, pairs. We need, the field and the conjugate momenta. The field here, the field and the conjugate momenta, there. Because, to define entanglement, you need a bipartition of the physical system. And, if you think classically, bipartition is a bipartition of the phase space in sub-phase spaces, each of them even dimensional, x1, p1, x1, p1, x1, p1. This is what defines a physical bipartition. If you just give me x1, x2, x3, you don't have bipartitions. You need canonical bipartitions. So to define both squeezing and entanglement, you need fields and conjugate momenta. Otherwise, there is no mathematical way of defining these notions. But we have not measured the conjugate momentum. The conjugate momentum of the field is proportional to the velocity, to the time derivative, and the scale factor. And we have only measured the field. The reason is because to measure the momentum, you need to measure the velocity, phi dot. And phi dot, if you isolate phi dot from here, you should move a to the other side. It goes 1 over a cube. And during inflation, a cube grows so much that the velocity goes to 0. So it is believed that we cannot measure the velocity, and therefore we cannot measure the momentum. So again, we cannot measure the momentum. The standard law is that we cannot measure the momentum because the velocity, which is what we can measure directly and infer the momentum from it, is extremely small and exponentially small after inflation. So we have only measured the field. Nobody has measured the momentum, and nobody knows how to measure the momentum. Therefore, without that information, we cannot make any statement about entanglement of a squeezing. We don't have enough information in the data to even formulate the question: is there a squeezing or entanglement in the CMB? We have only measured correlations. Again, just repeating myself, we have measured these correlations: field in pixel 1, field in pixel 2. And we cannot say anything quantum just from these correlations. Anything quantum, like a squeezing and entanglement, requires the conjugate momentum. These correlation functions can always be predicted by a classical theory. I repeat the sentence because I don't prove it, but it's true and it's very important. The correlation functions of the field in real space can always be exactly reproduced by a classical theory. So therefore, there is nothing genuinely quantum in this correlation function. You need conjugate momentum. You need something that doesn't commute with the field. And so far, we don't have that, and people believe we don't have access to the conjugate momentum. If that is true, we are screwed. So I'm going to finish here. Just let me read the main conclusions. So in my talk, I was addressing 2 points. One, my view on the discussion of whether inflation squeezes and entangles modes with wave number k and minus k. And second, the question, what we measure in the CMB and whether we can measure any entanglement and squeezing in real space in the CMB. So regarding the first point, the notion of squeezing and entanglement requires a choice of quadrature pairs. This is a simple observation, true in quantum mechanics. There is nothing like a squeeze state. You need to tell me which quadratures you refer to. For quantum fields in the expanding universe, there is no preferred choice of k and minus k. If you try to build Hermitian operators for k and minus k, there is ambiguity, and the ambiguity mixes them. So we are screwed. If one chooses to use the operators selected by the symmetries during inflation, as an example of a choice, one obtains that there is no particle creation and no generation of squeezing or entanglement. Because if you use the symmetries, and in general, the creation of entanglement goes hand by hand with the creation of particles. Therefore, only when there is a preferred notion of particles, you can obtain a preferred notion of squeezing. We only measure the field in real space, not the momentum. And this is insufficient to check squeezing or entanglement in the CMB. So all what we have measured in the CMB so far can be entirely accounted for by a classical theory. So if you find a way of measuring the momentum of the field in the sky, please give me a call because we have interesting work to do. And I want to stop here. And again, thank you for the chance to speak.
Okay, thank you very much, Ivan, for your very nice talk. And well, is there any question or in the audience?
Here, Adrian has a question.
Yes. Hello, Ivan. Thanks for the nice talk. So I have several questions, but I will go first with one, and let's see if I have time for the others. So when you say that there's ambiguity in the sitter because you can either use the symmetries or not, couldn't you do that also in Minkowski space, for example? Because you always have the choice of not using the symmetries, right? So this ambiguity is actually present in any case.
Right. It's a good question, and I tell you my feeling my answer. Maybe other people will have a different answer. I would differentiate between Minkowski and de Sitter. And the reason is that in Minkowski, you have time-like Killing vector fields, time-like symmetries. In de Sitter, you don't. In inflation, the extra Killing vector field is not time-like. And if you have a time-like Killing vector field, you can define a Hamiltonian, just contracting the energy momentum tensor twice the vector field, you obtain a Hamiltonian, which is time independent. And therefore, there is a ground state, physical ground state. And that ground state, has,
Okay.
is a very good candidate for the vacuum because it's the ground state. And therefore, it provides a preferred notion of particles. But in de Sitter, even though you have just one single extra Killing vector field, it's not time-like. So somebody could argue that de Sitter is not, the Miles-Davis vacuum is not as preferred as the Minkowski vacuum. So this is the difference. Whether you think that way or not, is a little bit up to you. I think the Miles-Davis vacuum is preferred by the symmetries, but I also keep in mind the difference with the Minkowski vacuum.
Okay, thanks.
Okay, may I ask a question, Ivan?
Of course.
Could you extend the analysis for other scenarios when particle creation is relevant, like, for instance, black hole radiation, and also for the Zwinger effect? I mean, the particle creation by an electrical time-dependent field. Because you were pointing out the fact that for the CMB you don't have access to part of the information related to the derivative, the time derivative of the field.
Right.
But now in other scenarios where particle creation is relevant, then we could perhaps bypass this problem and to say something. Well, it is not a concrete question. It's an open question.
I understand what you mean. Thank you for the question. The question is good. So let's consider the Hawking effect, for instance, just for concreteness. The Hawking effect is also special in the sense that we have these two asymptotically symmetric regions. The in region where you have, before the black hole has collapsed and you are very far away from the black hole. So you can use flat space symmetries to define the notion of in particles and the notion of in quadratures, and the same in the out region. When the black hole has collapsed and has settled down, you are really far from it. So in that case, you have preferred quadratures initially and finally. You can take the in vacuum and at the in the out region ask whether the state is squeezed and entangled, and the answer is yes. The answer is that with these preferred quadratures, the state is squeezed and entangled. But there, because field comes in the form of quanta of particles, you could take a particle detector, a photon detector, and measure these photons. Although in the Hawking effect, the problem is that the partner, the entangled particle, is inside the horizon. So even though in the Hawking effect you have access to both, X and P for your Hawking particle, you cannot check squeezing and entanglement because the partner is inside the horizon. So this is the specific problem of the Hawking effect. In the Zwinger effect, you could. In the Zwinger effect, because you have pairs and there is no horizon, you could measure both. And with a particle detector, you will have access to both position, the field and the conjugate variable. So there you could check this generation of quantumness in this process. In the universe, it's different because remember that we measure indirectly the field. We don't measure the field. The field, the field was inhomogeneous and provides, imprints the inhomogeneities in the CMB, which we measure. We are measuring indirectly the field via the photons of the CMB. So we don't have access to these primordial quanta, if you want.
Okay, thanks. Any other question or comment? Okay, so let's thank Ivan for this very illuminating and pedagogical. Okay.
So I don't know. Can I ask maybe one more question?
Yeah.
Okay.
Sure.
So maybe it doesn't make much sense, but I was wondering, like, I guess that you cannot mix in these quadratures. You cannot mix the K and 3K modes because of homogeneous, like special homogeneity. But is there like any intuitive physical meaning of what does it mean that K and minus K modes are mixing? Like, I mean, I don't know if, like, maybe the question is not very precise, but it was a bit surprising to me somehow.
Right. Because you really think of a particle. When I say a mode K, you imagine a particle moving to the right, and you say, how is possible that the particle get mixed with particle moving to the left? But this is why I was writing the Bogoliubov transformations. If you go to the way we define particles, to define particles, you need to make this choice of creation and annihilation variables. And and creation operators, they go with plane wave e to the minus I kx. But annihilation operators go with the conjugate mode, right? With the conjugate variable, which has an extra sign, e to the plus ik. But if you change k by minus k, creation and annihilation operators, creation operators of k and annihilation of minus k, they go with the same exponential, so they can mix each other. So I'm not very precise because I don't have a whiteboard, but what I want to tell you is that when you define creation and annihilation operators, this mixing of k and minus k is there, and that physically translates just to an ambiguity in the definition of particles, but mathematically mixes k and minus k. Yeah, answer is very clear. But
Okay, no, but I think it more or less at least gives me an idea of the origin. Thank you.
Okay. Thanks a lot, Ivan.
No problem.
Okay. So now our next speaker now is Lupamudra Sharma from the Indian Institute of Technology.
Hello.
Hello. Can you share your screen?
Yeah.
Now you are allowed to share your screen.
Okay, thank you.
You should have 4 buttons at the bottom.
Is my screen visible?
Not yet, but
Just a second.
just give us a few seconds to see if it charges.
Now is it visible?
It is loading. Yes, now we can see your screen. Yes.
Okay. Okay, so I'm starting. First of all, thank you for this opportunity to let me share about my work. And hello, everyone. My name is Lupamudra Sharma, and I am a master's student from the Indian Institute of Technology, BHU in Varanasi. And my talk is titled Stability Criteria for White Dwarfs in Palatini FR Gravity. So this talk is actually based on a recent work that I, along with Surajit Kalita and Aneta Wojnar, undertook in order to study the white dwarfs in modified gravity, or more specifically in Palatini FR gravity. And thereafter, we also checked how the stability criteria changes if we use this gravitational theory And then we checked that the famous stability we have this work is available on archive, and we have also recently submitted it in Physical Review D. So the motivation for our work actually came from the observation of the over and under luminous type 1a supernova. So these peculiar observations and sub-Chandrasekhar limiting white dwarfs can exist. And white dwarfs are basically stellar remnants, and they are supported by electron degeneracy pressure. So this electron degeneracy pressure counteracts the force of gravity and maintains the white dwarf. Now, but there is a limit up to which the white dwarf can do so, and that limit is known as the Chandrasekhar limit. So as you can make out from the name, it was discovered by Chandrasekhar, and the limit is at 1.44 solar masses. So once this white dwarf exceeds or reaches that limit, we get a thermonuclear reaction, and the white dwarf, it explodes in a very violent explosion, and that is known as the type 1a supernova. So because this type 1a supernova is occurring at that fixed mass of Chandrasekhar limit, that's why these supernova have a very characteristic peak luminosity. And since we are getting observations of over and under luminous type 1a supernova, so it is actually suggesting that maybe the Chandrasekhar limit is not unique as we thought. Now, actually the type 1a supernova is powered by the decay of nickel. And here I'd like to show you a paper in Nature. So this paper is actually titled The Type 1a Supernova from a Super Chandrasekhar Mass White Dwarf Star. And actually I want to show a plot here, this plot. So this plot is actually a plot of the nickel mass, which is on the y-axis, and the luminosity on the x-axis of the type 1a supernova. So for a typical type 1a supernova, the mass of the mass of nickel that a white dwarf should have is about 0.6 solar masses. And you can see this dashed line. So this dashed line is actually the upper limit for the nickel mass. And this means that if we have a model in which the whole 1.4 solar mass white dwarf is, it's exploding in a pure detonation, then the corresponding mass of nickel is around 0.9 solar masses. But in this plot, you can see this one supernova, isolated supernova here, and it has a luminosity of about 2.2 times more luminous than a typical type 1a supernova, and its corresponding nickel mass should be around 1.3 solar masses. So this suggests that this kind of an overluminous supernova cannot be originating from a Chandrasekhar limit white dwarf. So it's a possible candidate for this can be a super Chandrasekhar limiting mass white dwarf. Similarly, there are evidences of low nickel masses of about 0.1 solar mass. So a possible candidate for such underluminous type 1a supernova is actually a sub-Chandrasekhar limiting mass white dwarf. So our work is actually an attempt to unify this over and underluminous type 1a supernova with the super and sub-Chandrasekhar limiting mass white dwarf with a single theory. And thereafter, once we get these white dwarf in our modified gravity theory, we will look how this stability, how the white dwarf stability changes, and if the positivity criteria holds or not. So since all of our work is based on Palatini FR gravity, so I'll just briefly give a introduction about this Palatini FR gravity. So this is basically an approach to FR gravity, and in this particular approach, we consider the matrix and the connection to be independent of each other. Now, in our work, we have basically done all our calculations and derivations in the Einstein frame. And that's because the equations that we get in the Einstein frame are very convenient to use, and they are simple in nature. But the more physical frame is the Jordan frame, which is and both the frames are actually linked by a conformal transformation, which basically means a rescaling kind of a transformation. And using that, we can go from one frame to the other. So first, let's see the Jordan frame formulation. So in 2.1, we have the generalized action, where we have the FR. FR is basically the function of R, where R is the scalar curvature. And in our model, the form of FR that we have used is this, that's given in 2.6. So we have used the Starobinsky model, and we have used the first, a simplistic correction term, that's the alpha R squared term. So alpha here is our model parameter, and the value that we have chosen for alpha is such that it is not violating any solar system test. And we'll see later that depending on the sign of alpha, we can get both the regimes of super and sub Chandrasekhar limiting mass white dwarfs. And then we can vary the action with respect to the metric ones and get the field equation in 2.2. Again, we can vary the metric action with respect to our connection and get the field equation in 2.3. And in 2.5, equation 2.5, we have the structural equation, which is basically the trace of our field equation. And this is an important equation, as this equation will give us the form of our scalar curvature. Now, to go to the Einstein frame, we will first define a few quantities. So first we have this chi. So this chi is basically a scalar field. And if we just take the constant that our chi is nothing but the scalar curvature, then we can define another scalar field phi. Okay, so this phi will actually act as the conformal factor that will help to go from one frame to another. So using this, we can just write the action in the Einstein frame as given in 2.9. So you can see the quantities which are having the bar, they are in the Einstein frame. Means they are like the matrix G nu nu with a bar. So that is actually the conformal metric, and it's related to the metric in the Jordan frame by this expression that's in the highlighted region. So it's related by this metric in the Jordan frame by this factor phi. So again, the varying this action, we can get the field equations in 2.10 and 2.11. So now, in order to see if we are actually getting any kind of super or sub Chandrasekhar limiting mass white dwarf, we actually have to find the mass radius relation. Okay, so to do that, we need to solve what is known as the stellar structure equations. So these are basically consisting of the mass conservation equation and the pressure balance equation. So the TOV equations in Palatini FR gravity as well as the Newtonian limit were already been done or derived by Aneta in one of her previous papers. And in our model, we are actually considering the Newtonian limit because white dwarfs, though they are compact objects, but we can consider the field associated with the white dwarf to be weak in nature. And so we can approximately use the Newtonian limit. And if you use the conditions for Newtonian limit that's given in this highlighted region, then we end up with the then we end up with the stellar structure equations in the 3.1 and 3.2. So these are our stellar structure equations in the Einstein frame again. So you can see the quantities having a tilde on top of it. They are actually in the Einstein frame. So if you look carefully, then our stellar structure equations in the Einstein frame are closely, identical to the Newtonian hydrostatic stellar equations. But there is just a additional factor phi here, and otherwise both are they are very identical. Now again, to go back to the Jordan frame, we will just use the conformal transformation of in the radial coordinate r, and then we can go back to the Jordan frame and we get the equations 3.5 and 3.6. So the task is to now just solve these stellar structure equations with the help of our Chandrasekhar equation of state that's given in 3.3, and then we will get our mass radius relation. So let me just show you our mass radius plot. Yeah. So this figure 1, if you can see the figure 1 as well as the figure 2 are the mass radius relation that we got. So figure 1 is basically the mass radius relation in the Jordan frame, and the figure 2 is the mass radius relation in the Einstein frame. But interestingly, we got both the same mass radius relation are almost identical plots in both the frames, and that's because for white dwarfs, the conformal factor phi, it comes very close to 1. So quantities in both the frames are almost equal. So we get similar results here. So in this, let's see the figure 1 plot. And here we have just plotted the radius of the white dwarf and the central density with respect to the mass of the white dwarf. So as you can see, the various plots are corresponding to different values of alpha, our model parameter. And the central blue curve, that is actually corresponding to the original Chandrasekhar curve. And it's basically when alpha equal to 0. Because we can see from our form of FR here, if we take alpha equal to 0, there is no contribution from the higher order term, and we basically end up with the GR case. So that will give us the Chandrasekhar plot. And you can see that interestingly, all the plots are coinciding or overlapping in the low density regime. Okay, so this basically means that we do not have any significant contribution from the alpha R squared term or the correction term in the low density regime. So that also again we can check from the form of FR that we have took. So this R or the scalar curvature is, we can say that it is directly proportional to our density. So in the low density regime, the contribution from this alpha R squared term will also be very less. And so as a result, all the plots are coinciding in the low density regime. But you can see that after a certain density, that's about 10 to the power 9 gram per centimeter cube, all the plots are deviating from the central line. So the plots that are deviating towards the right, okay, so these plots are actually corresponding to positive values of alpha. And you can see that if we consider more positive value of alpha, then we get even larger deviation. So even though the plot have a usual trend of increasing mass with increasing central density, but it is overshooting the Chandrasekhar limit, and we can get a mass limit of as high as 2.2 or 2.3 solar masses. But if we look at the negative value plots corresponding to the negative values of alpha, we get a very interesting turn back. Okay, so the mass, it will keep on increasing with increasing central density, and it will reach a certain maximum value. After that, it will start to decrease with an increase in central density. So that's why we get a turn back of this sort. So here the positivity condition comes into play. So positivity condition is actually given by, this. So you can see this is the positivity condition. Del m by del rho c must be greater than 0. So this condition is actually valid in GR, and it basically means that the mass of the star should increase with an increase in central density. So, but if you look at this receding branch, we see that the mass is actually decreasing with increase in central density, and it seems like it's unphysical. So basically, we wanted to see if in Palatinid FR gravity, this branch is stable or not. Not only this branch, even the increasing branch is stable or not. And then we can do by what is known as the stability analysis. So here, let me just show you the stability analysis. Yeah. So a star in its lifetime is subjected to many kinds of perturbations. So this perturbation can either take the system away and away from its equilibrium position, and then we get a state of what is known as dynamical instability. Or else the perturbation can die out in time and the system can remain in its equilibrium position, and then the star is stable. So to find or to study the stability of the star, we need what is known as the radial oscillation equations. So in our model, we have considered that the perturbations are radial in nature. That means the star, even though it is oscillating, but it is maintaining its spherical shape. And not only that, we have considered that the perturbations are adiabatic in nature, means there is no kind of heat transfer. And lastly, we have considered our perturbation to travel like plane wave. So this in 3.15. So this is just our perturbation in a quantity f. So if we consider that this perturbation is traveling like a plane wave, then we can decompose it into a radial part and a time dependent part. And then the whole stability analysis is just to determine the nature of this sigma here. So sigma is the characteristic frequency, and we need to determine what is the nature of this sigma. For example, you can see if our sigma comes out to be real in nature. So if it is real in nature, then our perturbation will travel like a plane wave, and we get standing wave kind of a wave, and so our system will be stable. But if our sigma comes out to be imaginary, then our perturbation will either keep on growing with time or it will keep on decaying with time. But the more practical situation is to consider that the perturbations are growing with time. So then we will get the case of dynamical instability. So firstly, to derive our radial perturbation equation, we need to first perturb our quantities. For example, the equations from 3.8 to 3.10 are giving the expression for perturbed radial coordinate, perturbed density, and the perturbed pressure. And since we are considering the Newtonian limit, we do not take any relativistic, general relativistic effect into account. And so we have used the mass conservation equation and the conservation of momentum equation, and then substitute this perturbed quantities into our mass conservation equation in 3.11 and the conservation of momentum equation in 3.12. And then again, since we're considering plane wave kind of a perturbation, so considering everything, finally we get the radial oscillation equation in 3.16 and 3.17. So again, all this is in the Einstein frame, and we can again go back to the Jordan frame by the conformal transformation, and then we can end up with the equation 3.20 and 3.21 in the Jordan frame. So so now we just have to solve this radial perturbation equation and then look for the values of characteristic frequency or the sigma that are real. So that is actually our stability criteria. And to do that, actually, we have first defined what is known as a dimensionless frequency. So you can see here. So the dimensionless frequency is given by omega square, and is basically related to the characteristic frequency sigma square by this relation, where r is the radius of the white dwarf and m is the mass. So we have just taken a whole range of omega square, and only those values of omega square which are satisfying the boundary condition at the center of the star are actually the correct values of frequencies. So for that, we have just plotted omega square in the I think you are able to see this figure 4. So in figure 4, we have just plotted the range of omega square in the x-axis and the boundary condition at the center of the star on the y-axis. So the value of omega square which are satisfying the boundary condition at the center of the star are actually represented by minima. So they are giving the correct values of omega square, and then we just have to see if this minima is coming for a negative value of omega square or if the minima is coming for a positive value of omega square. So if the minima is coming for negative value of omega square, then we get a condition for dynamical instability. But if the minima is falling in the positive value of omega square, we get the condition for dynamical stability or stable configuration. Now, again, we have done the plots in both the frames, in the Einstein and Jordan frame, and we have ended up with almost identical results because of the conformal factor being equal to almost 1. And here you can see in the figure A, we have plotted for negative value of alpha, and in figure B, we have plotted for positive value of alpha. So first, let me just tell you about this figure A. So all the curves that you are able to see are actually corresponding to different central densities. So that's given in this box. And you can see that for low density regimes, for say up to 2 × 10⁹, all the minimas are falling after 0, means all the minimas are corresponding to positive value of omega square. That means all these white dwarfs are stable, and that should also be the case because in low density regime we do not have any contribution, any significant contribution from the alpha r squared term. But at high density regime, means greater than 10⁻10 gram per centimeter cube, the minima is falling for negative values of omega square in this red plot and this black plot. So that means what? These central densities are unstable, or these white dwarfs are unstable. And if we just compare it to our mass radius relation, we get that these central densities that we got to be unstable are actually on the receding branch. So they are also violating our stability criteria that omega square is coming out to be negative, and also they are violating the positivity condition. The del m by del rho c is less than 0 in this case. So these white dwarfs are actually unstable. Similarly, we have plotted for positive value of alpha in plot B, Again, all these different curves are for different central densities. And interestingly, in this case, all the minimas are falling for positive value of omega square. So all the white dwarfs in for positive alpha are coming out to be stable. But the interesting thing is that for greater densities, means for density greater than 10 to the power 10 gram per centimeter cube, the minima is shifting towards even more positive values. Means the high density white dwarfs in this case are even more stable than the intermediate mass white dwarfs. So again, we can compare it with our mass radius plot here. So we see that the high density or the more stable white dwarfs are actually in this increasing branch. And here the del M by del rho C is highly positive. So that's why we are getting that the white dwarfs in this case, or in the high density regime for positive alpha, is coming out to be even more stable. So in this way, we can do the stability analysis, and we can also check that in Palatini FR gravity, in the if we consider the Newtonian limit, then we can see that the positivity condition still holds. So so basically in our work, what we have done is that by changing the sign of our model parameter, we are able to probe both the super and the sub-Chandrasekhar limiting mass white dwarf, and then we have just studied the how this modified gravity is changing its stability of the white dwarf. So sometimes it is making the high density white dwarfs even more stable, or sometimes it is making the high density white dwarfs less stable. So as an extension to our work, we can take in more correction term in our form of FR, and not only that, we can the Newtonian limit of the TOV equation, but rather than taking that, we can use the full relativistic TOV equation and see how our mass radius is changing, or how the stability criteria is changing. And other than that, this can be the Palatini FR gravity theory can be used to study other aspects of stellar evolution and cooling models. So by this, I end my talk. Thank you for your time and attention.
Thank you for your nice talk. Is there any question, any comment?
Yes, I have a question, sorry. If I understood it properly, the equations that you are using to describe the star are more or less the same as in GR, and the difference arises in the equation of state that you have used. I mean,
the stellar structure equation or the stability equations?
The stability, no, the stellar structure equations. I mean, the one for the mass and the one for the pressure.
Yeah.
Yeah. And those are the same as in the case of GR. And yes. The differences with GR arises when using the equation of state. I don't know if.
Hello?
Can you listen to me?
Hello?
Hello? Sorry. Can you listen to me better now?
Yeah.
Okay, sorry, because the microphone is.
Can you please repeat your question?
Yes. Okay, so the equation that is for the star that you are using are more or less the same as in GR. And what changes from GR is when using a equation of state.
Yeah.
And I want to know if I understood it properly, how you did that. So, I mean, you choose an equation of state, like a normal equation of state for a white dwarf in the the Jordan frame, and then you put it in the Einstein frame, or how you did that?
Okay, so yeah. So basically, we have derived the stellar structure equation from the TOV equation. So Aneta, my co-author, she has actually derived these equations. So in Palatini FI gravity, we get the modified TOV equations. So it's given in A.5 and A.6. So these are the modified TOV equations. And if we just take the Newtonian limit, so Newtonian limit here, basically we have taken that this twice Gm is much less than R, then the pressure is much less than the density, and then we end up with our the stellar structure equations. Just a second. Here, yeah, 3.1. So these are actually more like closely identical to the Newtonian case rather than the GR case. And then we have used the Chandrasekhar equation of state to solve it in 3.2.
Okay.
So that's our equation.
What you are solving numerically is 3.1 and 3.2.
Yeah. Yes.
Okay.
With the help of 3.3.
Okay. So, for example, you could use, instead of this equation of state, another one. For example, one describing a neutron star, and more or less, it's the only thing that you have to do to describe a neutron star, no? Just changing this equation of state.
Yeah.
Because the other equations are the same. I don't know. I'm just asking, but I'm not sure.
If I can just add a comment, or Lupamudra, you want to finish your thoughts?
No, yeah, please, you can share your
So, okay, so in general relativity, so to study stability, you need to have an equation of state. And the stability of a star depends on the equation of state. There's a theorem, you can prove it and check and so on. But in modifier gravity, I mean, this is the same situation. So you can change your equation of state. You can consider the equation of state you like, and you can do the similar analysis. But apart from the equation of state, the stability also depends on the theory of gravity. So here we consider a particular model. So this is the Starobinsky quadratic term and so on, the modified field equations. So you need to check for each equation of state. You need to check, like, if you want to know, like, what is happening with a neutron star. So you need to have an equation for a neutron star and check for each equation of state. You need to check the stability condition for a given model of your theory of gravity. So the situation is more complicated because it depends not only on the equation of state but also on the model of gravity.
Okay. Thank you a lot. And thanks for your nice talk also.
Thank you.
Thank you, Lupamudra, for your very nice talk. So our next speaker is Alejandro Jimenez Kano from the University of Granada.
Hello.
Yeah, hello, Alejandro.
Let's see. Now you can see me, I think.
Okay, you can share your screen.
Okay, now do you see the document?
Okay.
And the pointer is visible?
Yeah, we can follow your pointer.
Okay, perfect. So, hello everyone.
Please, can you make it a little bit bigger? Just a little bit.
Like this?
Perfect.
Great. Well, hello everyone. Well, for me, it's always a pleasure to contribute to these workshops. Thank you so much, all of the organizers, and especially Gonzalo and Adria for the kind invitation. And in this talk, I would like to explain the basic ideas about this work done in collaboration with Jose Beltran about strong coupling problems in Einsteinian cubic gravity and generalizations of this theory. So here there are two things, the theories and the problems. So let me describe the basic idea of each of them. In the definition of the original formulation of Einsteinian cubic gravity, the definition of this theory is based on the existence of certain kind of spherical symmetric solution and so on. So the definition is not so relevant for our discussion. The important thing is that this theory has the same linear spectrum as general relativity around maximally symmetric backgrounds. And what I mean by this is that just the graviton is the only particle that propagates. These similar theories can be formulated higher order in curvature because this Einsteinian cubic gravity, as the name indicates, is a cubic, the Lagrangian is a cubic polynomial in the Riemann tensor. So we can formulate higher order curvature theories with more or less the same features. These are the so-called generalized quasi-topological gravities. These theories also have the same spectrum as general relativity, maximally symmetric spaces. Another thing that was done was to improve, let's say, this original formulation to another one. This is the cosmological, so-called cosmological Einsteinian cubic gravity. This theory now is again a cubic polynomial in the Riemann, but now it shares with general relativity the spectrum in any cosmological background, not only maximally symmetric spaces. So and there is no, as far as I know, no equivalent thing to this higher order generalization. So in this paper, in this talk, I'm going to focus on this improved version of Einsteinian cubic gravity, plus at the end of the talk, we'll consider some corrections of this quasi-topological type. Okay, so these are the theories. And you see that these are higher order curvature theories. They are not Lovelock. So in principle, these theories propagate generically more degrees of freedom than the graviton. Principally, generically, we have one extra spin2 massive, spin2 field, which is a ghost. Ghost means that the kinetic term has the wrong sign, and this is a pathology, this dynamical pathology. And there is also an extra scalar. So the thing is that these theories, in principle, contain these extra degrees of freedom, these potentially dangerous degrees of freedom, but around specific backgrounds, only the graviton propagates. And now I'm going to tell you why this is a problem. This is typically a problem. This is so-called strong coupling. Imagine that we have a theory with some degrees of freedom, and imagine that we have a background around which one of the degrees of freedom, for instance, this phi here, doesn't propagate. This means that the kinetic term, if we do perturbations around this background, the kinetic term has a 0 in front of it. So now let me consider a neighborhood around this special background, and let's consider a different background here, another solution of the theory, and let's do again perturbation. Since this new background this phi 0 is generic, in principle, this degree of freedom will propagate because it's a degree of freedom of the theory. So we will get some kinetic term with some function in front of it that depends, of course, on the background. And we know that this f vanishes when I select BG as my background to do the perturbation. Now, if we try to study the dynamics of this degree of freedom here, and we take if we want to study that, we need to do the canonical normalization. And here you see that when we approach BG, this 0 in the kinetic term becomes an infinity in all of the interactions. That's the reason why we call this strong coupling. Normally, this indicates, or this signals, that the perturbation expansion is not well defined around this point, or basically that when we do perturbations around this special background, this series is not capturing all of the information about the solutions. And this is also, as we will see in the particular example of Einsteinian cubic gravity, that this background lives in a singular surface in phase space. Okay, so the theory we are going to work with is, well, the Einstein term with cosmological constant plus this qubit combination. This is this cosmologically improved, let's say, Einsteinian cubic theory. And one can, and instead of studying general cosmologies, we're going to focus on flat cosmologies, okay, cosmologies with flat spatialist slices. One can find, for instance, the Sitter solutions in this theory, so on and so forth. But now let me skip the details and just go to the well, this is our BG, let's say, our special background, or strongly coupled, potentially strongly coupled background. And now we're going to, let's say, draw this neighborhood around it. Okay, so and the metrics we are going to use are these Bianchi 1 metrics. You see that for the case A equal B equals C, we recover the previous metric. So let's consider this Bianchi 1 metric. One can construct the isotropic Hubble parameter, and we also introduce here this sigma 1 and sigma 2, which basically encode the information about the anisotropies, the deviation with respect to the isotropic solution. We also use this parameter here to control better this isotropic limit. And now, well, another interesting thing about this metric is that it, with this non-trivial lapse here, it fulfills the requirements of the Paralyzed principle of symmetric criticality. This basically tells us that evaluating the ansatz and varying, namely obtaining the equations of motion, these two processes commute. So we can first substitute this in the action, and then obtain the equations of motion with respect to n, a, b, and c, and then, well, that's equivalent to first varying, get the huge equations, because you can imagine that the equations of this theory are huge, and then substitute the ansatz. So it's quite convenient. Okay, and so at the end, after using the Bianchi identity of diffeomorphisms and so on, at the end we end up with just 3 equations. The equation of the lapse, this is the generalization of the Friedman equation, and 2 evolution equations. These are the equations of motion of the anisotropies. Okay, let me now focus on these last 2 equations. Let me skip this part. We will come back later. This is the general form of these equations. You see that this is a third order in derivatives system of differential equations. But remember that these sigmas are basically, they go with the derivative of a, b, and c. So this is actually a fourth order system of differential equations for a, b, c. And the interesting thing here is that these 2 terms, the highest derivative terms, are proportional, or are of 1 order in epsilon sigma greater than the rest of the equation. So you see that when we evaluate here the isotropic background, something highly non-smooth happens, that the rank in derivatives of the system of differential equations abruptly goes from 4 to 2. And this is typically problematic, and the problems can be seen in the as we will see now, in the perturbations. Let me first give you an example. Imagine, so you can see this better. Imagine that you have an equation of this type, third derivative, second derivative, up to some coefficients here, irrelevant, and the highest rank term has some function of f in front of it, and such that this a is 0 when evaluated in the background. This is basically what is happening here. You see, we have this epsilon sigma here, which is 0 in the isotropic limit. Now we perform perturbations of f and a, and you can see that at 0 order, the third order term drops from the equation. We get a second order differential equation. We can solve it, obtain f0, and then at the next order, again, the highest order derivative term disappears. Here we have another one, but this one depends on the function that we already got. So this is not the unknown of this equation. So again, we get a second order differential equation instead of a third order differential equation. And this happens order by order in perturbation theory. So you see that it's like the information about this higher order term in derivatives disappears, or is transparent in the perturbations. This is exactly what one can check if you take, for instance, the Sitter solution of this Einsteinian cubic gravity and do perturbations around the Sitter. The first order system of equation is this one. You can see that the fourth derivatives and the third derivatives don't appear here. And the same happens at the next order. This is basically signaling that this perturbation solution that we are obtaining order by order is not, again, capturing all of the information about the solution. And in order to see this better, because of course this cannot be like done at all orders, because it's an infinite process, I invite you, if you're interested in the details, you can download this paper and go to the end. Here in this appendix, Jose Beltran designed a differential equation, a very simple differential equation with a similar behavior. And here we do the perturbations, and you see that the solution you get from perturbation expansion is not the general solution of the theory. This has to do with the background around which you are perturbing is lies in a singular surface of the space of solutions. This is quite interesting. So now let me, we are here. So now let's move on, and let me, well, first I'm going to use this X and this Y. These are nothing but the sigmas, the anisotropies up to some functions and global function. And one can compute the principal part of the system of differential equation and see which are the surfaces in which this principal part is singular. One can draw these surfaces. These are these lines here, these color lines. And this blue dot, the center, you see it's the point with zero, both zero anisotropies. This is the isotropic solution. These diagrams, well, these two and these two correspond to different values of this combination here, this parameter. And the right diagrams are just zooming in this region close to the isotropic point here. The instability is evident. The direction, you can see it in the direction of the flow. Here it's maybe more obscure. You see that there is a line in each of these sectors that come back to the origin, but the rest of the flow ends up in these singular surfaces. So you see here clearly the I wouldn't say unstable or not unstable, but pathological behavior here close to this point. And indeed, this can be seen in particular examples if we do some numerical simulations. Here we took the de Sitter solution of the theory, and we take the full system of differential equations of the theory, and what we did was, well, this black line is the exact solution. You see the unperturbed solution. This is H constant, this is de Sitter. And in this second diagram, I have sigma 1 and sigma 2 in orange and red. Here you see different values of sigma 1 in different initial conditions and the evolution for sigma 1 and sigma 2. And here the blue lines are the represent the evolution of H with the same initial conditions as for the exact solution, but with these anisotropies you have in the right plot. And you see clearly how these lines diverge from the exact behavior. At the end of this, at the tips of these lines, the program stops integrating. This basically signals that we are very, very close to these singular surfaces here. And we repeat this same analysis for a different regime. Here we neglected the cosmological constant, and we assume that there is some radiation, some perfect fluid of radiation in the universe. We found the numerical solution now in terms, instead of the time, in terms of the number of e-folds. And here you see more or less similar behavior. You see this, the important thing is the divergence between these two behaviors. Okay, so that's all of this, of course, was for Einsteinian cubic, just for Einsteinian cubic. And now in the last part of this paper, what we consider is, well, basically adding 3 more terms to the action, the 3 first generalized quasi-topological gravity. Here it's important, let me remind you that the Einsteinian cubic gravity we are considering as this strong coupling problem in cosmology, because this is the special background around which only the graviton propagates. But for these quasi-topological theories, general quasi-topological theories, this only happens around maximally symmetric spaces. So here we expect something slightly different. And indeed, when you compute the equations of motion, here you see that when we evaluate around cosmology, isotropic solution, only this part disappears, and we have an extra contribution here that survives. This you see that this is a non-trivial contribution from the highest order derivatives, and this implies that you need more initial conditions, and this in the Hamiltonian formulation of Ostrogatsky, this represents that you have more degrees of freedom that indeed propagate with the wrong kinetic term. This is, of course, showing that around cosmologies, the ghosts propagate in this theory. Of course, if we go to cosmology, which is maximally symmetric, we switch off this epsilon and also h dot, we go to the sitter, again, we recover the strong coupling. All of this part goes to zero. Okay, so that's basically so you see that this combination, when we add these terms, the situation is more pathological because the ghost now can move and propagate in the theory and interact with the rest of the fields. Okay, so I don't want to bother you with more stuff. Just let's say the conclusion or the idea one can extract from this analysis is that when we design models, or when we find solutions and do computations around them in modified theories of gravity, it's always important to check if the degrees of freedom propagate correctly, and if the perturbations we are doing don't, and ensuring that these perturbations don't like render pathological degrees of freedom that are hidden somehow and that can interact strongly with the rest of the sectors of the theory. And regarding future prospects, well, these techniques can be applied to other theories or to the same theory but different backgrounds. For instance, spherically symmetric solutions, which are like probably the core of these theories, is non-hairy black holes and so on. So that's basically all. Thank you.
Okay, thank you very much, Alejandro, for your nice talk. Is there any question or comment from the audience?
I have one. Okay. My question is about isotropy. I'm referring to the fact that in GR you get isotropy when you put matter, no? In vacuum you don't get isotropy. So in your model, what happens? Which are the differences between the vacuum case and the matter case?
The matter. Well, here this is. I'm not sure if I understand the question.
In the sense, just considering the Bianchi one case in GR, no? Vacuum, this model does isotropize, just remain with an isotropy. When you put matter, like for example dust or whatever, the model gets isotropy. In these kind of models of Einstein cubic duality, what happened?
I don't know.
Because I saw your graphics regarding the sigma 1 and sigma 2 functions that I saw that are constant basically for a large amount of time. So it seems to me they then don't get to zero.
So you say that I have to add anisotropies in the matter sector also? I don't know if I am.
Yeah.
Yeah, probably. It's a good point.
Okay, more questions? Okay, if not, thanks a lot, Alejandro, for your talk.
Thank you.
And now we are jumping for the final talk by Mariam. Mariam, can you hear me?
Yes, I can hear you.
Okay, thank you. Can you share your screen? Ah, fine. Okay, you are.
Okay.
Now you should share the screen.
One moment. Mhm. Can you see it now?
Now, okay, fine.
Okay, thank you.
Okay.
So first of all, I would like to thank Gonzalo for the kind invitation and all the organizer, and also for changing the time of my talk at the last minute. At the last minute, I knew that I could not speak yesterday morning, so I'm thankful that he changed my talk to this afternoon. Okay, so the talk I will give is about three forms, and in particular how they could describe the late-time acceleration of the universe. And given that late-time acceleration that can be driven by some three forms with some specific potential, could it use such an acceleration, okay, such repulsive effect, gravitational effect, then maybe that's a way of getting or of smoothing the singularities that are present in black hole, and also could be the base to have wormhole solutions. So that's the main idea that I will try to convey on this talk. So let me start. Essentially, I will give a brief introduction about why do we know that the universe is currently accelerating, and then I will give the simplest example in which this acceleration is driven by a cosmological constant or some fluid with some constant equation of state. And then I will move on to describe this acceleration by something that I would say is more fundamental, like could be the case of three form, okay? And then I will, on the fifth point, I will see how, well, for some three forms, we can get regular black hole, which mimic from the outside, it would be like Schwarzschild, but then the inside would be quite different. And also how these three forms could be also the support for some wormhole solution. Okay, and then I will conclude. So the introduction, so we know that the universe is homogeneous and isotropic on large scale. So this is essentially the cosmological principle. Can you see my mouse if I do this?
Yes.
Okay, thank you. Then we know that only a small, tiny part of that matter is standard, and the rest is dark, on the sense that we see it only through its gravitational interaction. Okay, so that's dark matter, roughly 1/3, and the rest is something that, since the universe was roughly half its current size, well, it induced its acceleration. How do we know that? Well, from an observational point of view, essentially, because supernova, as was discovered by the late 90s, they look fainter than they should, okay? So this means essentially that they have traveled a longer distance, okay? And if they have those explosions that's like that we see has traveled a longer distance, this essentially means that the universe is expanding at a higher rate. Those observation has been backed up by other observation, like the measurement of the Hubble rates at different redshifts, at different period in the evolution of the universe, through the baryon acoustic oscillation, also through the cosmic microwave background, and also through the larger scale structure. So for example, through the matter power spectrum and the growth function. So for the matter power spectrum, essentially we are looking at different scale and how matter behaves at those scale. For the growth function, essentially, we fix a scale and see its evolution at different redshifts, okay? Now, the simplest way to describe, as I said, the acceleration of the universe is essentially by invoking a constant equation of states, and that is done through the model W called dark matter, okay? It's a purely phenomenological model. Well, W equal exactly to -1, where W is the equation of state for dark energy, would be the ratio between its pressure and its energy density, and that value has to be smaller than is roughly of the order of -1. It could be larger, it could be smaller, okay? But essentially is close to the value -1. Now this from a phenomenological point of view. Now that acceleration, well, it could be due to two effects. Either we have a new component that we don't know its true fundamental nature, and that means essentially that we add some new budget into some energy into the budget of the universe through dark energy, for example, like in W called dark matter, or we can have something that evolve, a scalar field that is evolving. It can be quintessence, many other things, all of three forms, as I will mention. Then there is an alternative way, which is essentially that gravity, at some scales, it deviates from GR, okay? And there are plenty of models that try to describe the late-time acceleration on that way, either in the metric formalism or the affine-metric formalism, okay? On this talk, I will stick to this point, okay? That there is a dark energy, that there is a component on the energy momentum tensor of the universe that induces this late-time acceleration, okay? Now, let's go to the simplest case if what we have is a constant equation of states, okay? W called dark matter model. So let me go to basic things. So if we go to the Reichholder equation, which essentially states how does the size of the universe, the acceleration, let's say, how does the universe accelerate? Well, that is related to the matter content. And nowadays, essentially dominated by two components. One is dark matter plus normal matter, which is a little bit radiation. I didn't put it there because it's too small nowadays. And then another component, which will be dark energy. Now, if we want this term to be positive, given that we have a minus here, so this means essentially this term here has to be negative. Okay, so the strong energy condition has to be violated so that we have acceleration. So that doesn't come as a surprise to us. We know that in inflation, indeed, this what happened. In addition, observation indicates that this W dark energy, which is essentially the ratio between the pressure, dark energy, and its energy density, has to be roughly of the order of -1. Okay. Essentially, when this term start dominating, then this term will become positive and the universe will start accelerating. As I said, the simplest case is lambda CDM, lambda cosmological constant, or W called dark matter, which means essentially that the ratio between the pressure and the energy density is constant. Okay. Now, this, from a background point of view, can be described easily by using a cosmographic approach, and in particular by using the state-finder approach that was introduced by Sahni, Saini, and Starobinsky back in 2002, which is essentially a very smart way of rewriting the cosmographic parameter. So what does this mean? So essentially what the cosmographic approach does is you have your scale factor, which depends on time as the size of the universe change as the universe evolves, and you make a Taylor expansion, what is usual in physics. Now, the smart approach that Sahni, Saini, and Starobinsky followed was that they rewrite this Taylor coefficient, okay, in such a way that for lambda CDM, which means essentially cold dark matter and a cosmological constant, those parameter gives always the value 1, okay? This means that as soon as we move from lambda CDM, so those value will be different from 1. And that is essentially what is plotted on this graph. So we have here S4, which is related to the fourth, to coefficients that goes up to the fourth derivative of the scale factor, S3 coefficient that go, they are exactly related to the third derivative of the scale factor, normalized properly to the Hubble rates at present, okay? Should be a 0 here, I'm sorry. And then S5, which is related up to the fifth derivative of the scale factor, okay? So when we are exactly lambda CDM, so we are essentially on the point 1, 1, okay? So if, in addition, we take into account that, of course, we have small amounts, a very tiny small amount of radiation. So of course, while nowadays that amount is tiny, if we go back into the past, so it will have some influence. And then we have two other curves, the red one, okay, and the blue one. So the red one would be lambda W cold dark matter with an equation of state slightly smaller than -1, while the blue one is the W cold dark matter with an equation of state slightly larger than -1. So these three models in the past, given that dark energy does not dominate, so the three line overlap. Okay, as we move into the future, okay, so this line will diverge. So here, what's essentially what I'm trying to convey is that this idea by Sahni, Saini, and Starobinsky of a proper representation of the cosmographic approach could help us when right now the measurement can go up to the coefficient Q, which is the second derivative of the scale factor. So when that is observationally that would be possible, so we could distinguish the behavior of different, from a background point of view, of different dark energy model. Okay, so that was the goal of this slide. So that's from a background point of view. What about the perturbation? So the perturbation, in this case, we'll be working in GR. So essentially, we can work on the Newtonian gauge, which essentially the two scalar perturbation, okay, so they are equal. And so if we look for one perturbation at a given mode, so here it's represented by this index K, which is essentially the scale at which we are looking at the observation. So in this case, for example, the value 10 to -3 megaparsec, -1 was chosen. Okay, so by looking at those different Fourier modes for the gravitational potential in the Newtonian gauge, for the delta M, which is essentially the perturbation on the matter sector called dark matter, respect to the background value, normalized in this case to the initial value of the gravitational potential, and also the perturbation on the dark energy, if the dark energy is evolving on time. If we were in lambda CDM exactly, that perturbation would be exactly 0, which would be this line. So let me go step by step. So on this first slide, so what we have is the gravitational potential at a given mode, K, in this case, as I said, 10 to -3 megaparsec -1, and for 3 models like before. So we have the red one, an equation state slightly smaller than -1 exactly lambda CDM, and the blue line, so which is an equation state slightly larger than -1. So 0 means the present, okay? So essentially it's the log of the scale factor respect to its current value. So this line would be the present, that would be the past, and that would be the future. So these three models are quite different asymptotically in the future. So on the case of lambda CDM, this perturbation, gravitational perturbation, will go asymptotically to 0. On the other two cases, they will go to a constant. In one case, 0 there would be for the red one, which is an equation state smaller than -1, which means that it has a phantom behavior. So the gravitational potential will flip somehow its sign, which means that the structure will be destroyed in the future. While in the other case, it will go to a constant. Now, for the perturbation delta M, we see that they are essentially the same. We can compare relative to the lambda CDM model, okay, essentially by making the ratio of the two. So we see that delta M is slightly larger in phantom-like model and slightly smaller in quintessence model. Finally, for the perturbation for dark energy, so of course, if we are exactly in lambda CDM, okay, so there are no perturbation by definition, okay, because the cosmological constant is constant. Now for the other case, so essentially the perturbation will have different signs. So in one case positive and the other one will be slightly negative, okay? So this is from a background point of view summarized on these slides, and the perturbative part summarized on this other slide, okay? Could this model, of course, because at the end what we need is to check if they can describe the current evolution of the universe. And yeah, it's known that this three type of model can describe the evolution of the universe. Here I'm putting just from a perturbative point of view, which I mean, that essentially by plotting F sigma 8. So F is essentially how does the perturbation on matter evolve respect to the size of the universe for a given scale, which it is K sigma 8, okay? Whose value is written here. So as we can see, so the three model, of course, they fit the data. Okay, so this, as I said, as an introduction, the simplest model to describe the current acceleration of the universe, a constant equation of states, which can be slightly smaller than -1, exactly -1, or slightly larger than -1. Okay, now the rest of my talk, well, I will focus on three forms. First of all, how these three forms could describe the acceleration, the current acceleration of the universe. But first, let me say why they could be important, okay? So they have been in physics and in the market for a long time. The first one, well, I missed it here. I should have added here another reference back in the 80s. So aside from the paper by Turok and Hawking, so it was related to the fact that the three form could help to solve the cosmological constant problem, because as we will see later on in the equation, it mimics exactly, in absence of potential, or if the potential of that three form is constant, it exactly mimic a cosmological constant. Okay. It has been also analyzed by Copeland, Lahiri, and Wantz back in the 90s in the context of string theories. Okay. Then later on by Tomiko Visto and Nunes, among others, it has been invoked to describe the early inflationary era and the late time acceleration of the universe. And it is on this context that I will invoke the three form, as I will show in a moment. Also, it has been analyzed by Kumar during his PhD with other collaborator, Nelson Nunes, Marta Moniz, and also Murray, the non-Gaussianity effect. Okay, of course, as we have heard on the first talk of this afternoon, so we don't see those non-Gaussianity. So in principle, those models that invoke two, three forms as a way to describe the early inflationary era, so they are kind of, let's say, drawn out. Some three forms could induce singularities, and that's what we analyze in a work with David Rizuela and Iñaki Garay. Okay, so here, as I said, so we'll see how can we use these three forms to describe the late-time acceleration of the universe, and in particular, if you allow me, I will go back. How can we get something that gives us an equation of states slightly smaller than -1? Okay, but without changing the sign of the kinetic term, okay? Like as it has to be done if we invoke, for example, a scalar field. If we want an equation of state slightly smaller than -1, which means that it violates the null energy condition, then the kinetic term has to be, we have to change the sign of that kinetic term. This is not needed in the case of a three form, as I will show in a moment. But let me first start reviewing what are these three forms, and in particular a P form in a d-dimensional spacetime. So a P form is a totally, sorry, just one moment. A P form is a totally antisymmetric covariant tensor, like this one here, and those brackets means that those index are antisymmetric. And if we are in a spacetime of the dimension, then the number of degrees of freedom that a massive P form, which means essentially a P form which has a potential, is given by this expression, d -1 factorial, d -1 p factorial, p factorial. This means essentially, as we will see on the next slide, that if we are in form dimension as our spacetime, then a three form has 1 degree of freedom, the same that would have a scalar field, and therefore it's the simplest way to go beyond, let's say, a scalar field. Well, beyond maybe it's not a proper. If we want to have the same degree of freedom as if we have a scalar field, so another option would be three form. Indeed, so if we are in a four-dimensional space-time, so if we have a scalar field, is essentially a zero form. The P1 is a vector field, and it has 3 degrees of freedom. And if we P equal 2, so we will have a 2 form, and finally P equals 3, we will have 1 degree of freedom, 3 form. Okay. Now you say, can we have dynamic with a 4 form in a 4-dimensional space-time? And the answer, unless if there is some coupling with gravity or something, the answer is no. Essentially, what happened is that if well, if we are in a, let's say, in a four-dimensional space-time, if we take the covariant derivative of that four form, that will give us in principle something with 5 indexes. But if we want to make it antisymmetric in a four-dimensional space-time, we'll get a 0. Essentially, that's why that would not have a dynamic. So we'll not have a four form in let's say, that would get some dynamic. Okay, so we can go up to the 3 form. I hope I made myself more or less clear. Okay, so the action that can describe 3 form would be this one written here. So F would be the 4 form, which is the exterior derivative of the 3 form. Okay, so what I was trying to say before, if I take here the exterior derivative of the 4 form, that will give me 0. So I will not have a kinetic term for that 4 form, unless if I couple it to something else. But well, let's make here things as simple as possible. So the 3 form would have an action in a 4-dimensional space-time this way. So this would be the kinetic term, which is given through the 4 form, which is nothing else but the exterior derivative of the 3 form. And here will be the potential. Now, why were the 3 form so important back in the 80s? So essentially because if this V is constant or is 0, okay, this term is 0, so essentially this means that this thing here would be constant. Then if I go back here, so that will give me, naturally a 3 form will give me a cosmological constant, okay? And if it gives me a cosmological constant, so that already is telling me that somehow it drives the early inflationary era or the current acceleration of the universe. So let me go to the simplest case. If we are in a homogeneous anisotropic universe described by Friedman, Limit, Robertson, Walker metric, like this one, then as we said, there is only 1 degree of freedom associated with that 3 form. And the only non-vanishing components are those that have indexes corresponding to the special parts, I, J, K. And that degree of freedom is encoded on this function chi of t. Okay, so that chi of t will be evolving. Okay, depending on the potential that we have. The Friedman equation, or the 0, Einstein equation, will give us the following. So if we have only a 3 form, so the equation of the Friedman equation will be the following. So here is the kinetic term. Okay, so that term is essentially the one coming from, no, sorry, here I didn't write the, well, it's the one coming essentially from this side, the kinetic term, and plus this other term, which is the potential one. So the construction of the 3 form is itself. Notice that there is a difference with respect to a standard scalar field, and is this term over here. And that's what makes the dynamic of the 3 form different from the one of a scalar field. Okay, now why could this 3 form describe or mimic phantom-like behavior? So because although they have the right kinetic term, so you can see here plus, now the sum of its energy density plus pressure is proportional to the derivative of V respect to essentially chi square, okay? Because I can multiply up and down by chi, and here this essentially will give me V respect to the derivative of chi square. What does this mean? This means essentially that we have a minus here. So if this term here is negative, which means essentially that the potential is a decreasing function of the square of the 3 form or of chi square, then if this term is negative with this one positive, then this will lead naturally to something like that has an effective equation of state smaller than -1, okay? The equation of motion of the 3 form are different from that of a scalar field, essentially due to this term here, or said in other words, you can see it also on the Friedman equation because of this term here. Now, in order to compare or to get some intuition about the evolution of these 3 forms in a homogeneous anisotropic universe, oops, I'm going a bit slow, about a homogeneous anisotropic universe, so essentially what we can do is to use this Reichholder equation to rewrite the evolution equation of the three form. So such that we write these as some derivative of an effective potential. And then as we know, or we have further intuition or better intuition about the motion of a scalar field, then we can apply that intuition to the case of three form. And this is what is done here. That was done by Nelson Nunes and also by Tommy Kovist. So essentially they rewrote. Yes.
Can I ask you a clarification?
Yes, sure.
Can you go to the previous slide? The last equation, you said that is not the equation of a scalar field because the third term, but could you mimic that with a scalar field which is not minimally coupled to the curvature?
Which is not minimally coupled? Probably, maybe. Minimally coupled for sure, because that term will be absent.
Right, because it's H dot, which has to do with A double dot and the curvature. Yes. I was wondering if you can get something like that, tuning the coupling to the curvature.
Just one moment. I remember in an old paper when I was a postdoc with David once, we had some, it was a brain wall model, but anyway, the equation of motion are similar. And
I don't want to break your
dot, but not exactly. It's not as, let's say, as clean as here. So there was H dot and other thing. I don't know by heart the equation. I should check it too. But okay, yes, okay. They could. You can have H dots plus, but not as clean and as symmetric as here. You can see here, H chi dot, H dot chi. It was not as simple as that.
Thank you.
Welcome. Okay, so as I said, to get some intuition, so one way essentially to rewrite the equation on this way, or said in other way, you can imagine that this is some kind of effective potential. Understand that all that term, the green one plus the black one, you write it as derivative of V respect to, derivative of V effective respect to some kind. So there is a difference with respect to minimally coupled scalar field. And the difference is that these two limiting points, this chi c, so I didn't write here what's its value, it's related to the gravitational constant, okay? Kappa square is 8 times pi j, okay? So we have the critical points, or the fixed points associated with the extrema of the potential, plus these two critical points, okay? And then we can have essentially two types of behavior. Either the potential grows with the square of the three form, or it decays with the square of the three form. I'm insisting on the square of the three form because the potential is V of A3 indices, A3 in this button. So it's always chi square. So it's symmetric. So we can have those type of behavior, and that was already analyzed by Tommy Koivisto and Nelson Nunes. And what they realized was that through a dynamical system analysis, so essentially, in this case, if the potential is a growing function of chi squared, it goes to the minimum, okay? On the other hand, if the potential is quadratic with chi square, is a decreasing function with chi square of the three form, then essentially the three form will end up in these 2 points. This can be seen through the effective potential plus minus a constant, because what we have is the derivative of V respect to chi, or V effective. So that V effective would be this one, okay? And on this case would be this one, the green plots. So in this case, essentially what happens, somehow it has enough kinetic energy, it reached the top, blonde, and then it ends up here. While in this other case, so essentially the three form will go up to here, okay? Maybe it can reach if it has enough kinetic energy, but at the end it will end up on this point or on this point. And those 2 points are essentially those values chi c. And they are quite peculiar. That's what we did with João Marto, João Moraes, Sravan, Kumar, and also Yasir Tavakoli. So these 2 points what we realized was that they were quite peculiar, is what we call the little signal of the big rip. So essentially something much smoother than a big rip. And once it's not a singularity, because first of all, it takes an infinite cosmic time to reach there, but essentially here the curvature blows up, okay? Now, for this kind of potential, it can be shown that we can describe the acceleration of the universe, okay? And that's what is shown essentially here. And in particular, they can fit F sigma 8 and data. I put it briefly as I have still, I would like still to speak about regular black hole, three form, and wormhole. If you have further interest on this, I think I can put somewhere the paper, hopefully. Well, I think I forgot to put the reference. Anyway, if somebody wants to know more details about this work, just let me know and I can give you the reference. The other two work I wanted to speak about is regular black hole in three forms, something I did recently. Zeyushen, Yon, and Dehamyon. Okay, and also about how we can construct wormhole with three forms. Okay, with the same author. This part, I'm sorry, I will have to. How much time do we have left?
Like 15 minutes, 20.
Oh, okay. So then I have time. So as I said before, these points could be, well, they correspond to little signal of the big rip. They are not exactly singularities, but somehow the curvature blows up there. Okay, so if the curvature blows up there, then we will need some quantum cosmology to describe it. Unfortunately, we don't have a fully consistent quantum cosmology approach, but there are several approaches. So yesterday we heard a talk by Param, in which he was making reference to some loop quantum cosmology approach. Here I will briefly mention another approach, which is different. It has its limitation. I'm not saying that it doesn't. And it's the one based on the Wheeler-DeWitt approach. So essentially, here the idea is to describe the evolution, the quantum, let's say, description of the universe would be described by some wave function, and that wave function fulfills some differential equation, which is this Wheeler-DeWitt equation. So essentially, as I wrote here, the equivalent to Schrödinger equation. Okay. The field of quantum cosmology on the framework of dark energy singularities or late-time singularities has been led on the last year by Klaus Kiefer, and we have done some work with him. So here I will briefly mention what happened for a little signal of the big rip, which is essentially that kind of abrupt behavior that can induce a three-form. Okay, and for simplicity, I will stick to the case of to a scalar field. In this case, of course, the scalar field has the wrong kinetic term. So it has a minus here and a minus here. And it can, if we have a little signal of the big rip, so that potential is essentially quadratic. So it's a phi square with some constant. And that constant essentially measure the deviation of the scalar field from a cosmological constant. What I mean by this essentially is that P plus rho effectively would be a constant, minus a constant, and that constant is essentially that A, okay? The same thing can be done for the shape bell potential for the three form. But here, as I said, for simplicity, I had this slide, so I used this one. So the Wheeler-DeWitt equation would be this one here, and it would have a plus instead of a minus, and that is coming from the fact that it's a minimal cap scalar field with the wrong kinetic term. Briefly speaking, so for those kind of behavior, and in particular for the little signal of the big rip, so what happened is that the Wheeler-DeWitt equation can be solved within some approximation. This cannot be done exactly, and in particular using the Born-Oppenheimer approximation, which means essentially that the gravitational part, which is the one that depends on alpha, or the log of the scale factor, which is that alpha, is has essentially an oscillatory or an exponential behavior. While the matter parts, once we make this decoupling, as described by the Born-Oppenheimer approximation, which means essentially that this part, the gravitational part, is much more important than the matter parts, then so essentially on the gravitational side, what we have either oscillation or something that is increasing or decreasing, okay? And on the matter part, so we have some kind can be solved exactly, and that's described by some parabolic similar function. But I will not enter into technicality here. The message that I would like to transmit, essentially, that there are subsets of solution where this function phi that depend on the geometry, so the scale factor alpha and the scalar field, such that that wave function goes to 0 when the little sigma of the big rip is approached. And that can be interpreted by the fact that the DeWitt condition is fulfilled, which means essentially that the abrupt events can be avoided, okay? For the work on 3-form, you can see this paper over here with David Rizuela and Iñaki Garay. Then for the f of r case, it was a work we did with Theo that gave a talk yesterday, and with Prado Martimor, okay, in f of r metric theories. Now, for the last part of my talk, so essentially what I will try to convince you is that, well, with these 3-form, given that they have some repulsive effect, so that repulsive effect can be so strong that we can get regular black holes, and we can also have wormhole solution. Now, why would we that importance on the case of black holes? So we know that GR predicts the existence of singularity, like those of black holes, and it seems like there are plenty of black holes around us, even at the center of our galaxy. Now, on the other hand, and that's what I want to insist here on this talk, about 70% of the current matter content of the universe is on the form of dark energy, if we believe that is indeed a new component or that induced that singularity. And that new component is compatible with phantom dark energy, okay? Not only that, it could also alleviate the tension that is present in H0, which means essentially that those measurements of the Hubble rate inferred from things that happen relatively close to us, relatively close, a way of saying, I mean, for example, through measurement of supernova, so redshift is very small. Well, it seems that it's is larger than those that we infer from CMB, so that H0 is smaller. And those phantom dark energy could, among others, somehow alleviate the tension on H0. So given that we have 70% of that content of the universe nowadays, which could be of phantom nature. So phantom nature is a very repulsive effect, okay? Now, if we have that very repulsive effect, and at the same time, we have singularity that happen in GR, which is the opposite effect, so could these repulsive effects help us somehow to solve some of the singularity present on GR, and in particular, those present in black holes? So that's what I will try to, well, convince you here. To this regular black hole. And of course, wormhole, because wormhole close to the mouth, they need matter that mimic phantom behavior, that violate the null energy condition. And imagine if 70% of the current content of the universe, well, has that effective behavior. Why we would not have wormhole solution? So black hole with 3 forms, and also for wormhole, so I should have added here another reference of this year by Lobo and collaborators. So they have already analyzed black hole solution, but they were mainly interested on the exterior. So they followed an approach different than the one I will describe here. So here we are rather interested on black hole solution, which are regular, so essentially, so from the event horizon inside, can we somehow avoid that singularities? So inside the event horizon, if the space-time is static and spherically symmetric, So it can be described by a Minkowski such anisotropic matrix. So it's like if we had a universe in a shape of rho b. So we have two scale factor, A of t and B of t. Okay. Now on top of that, so I will assume that the matter sector is described by a 3-form, and that 3-form, that degree of freedom will be encoded in chi. Okay. Now, the other thing that we assumed was that close to the event horizon, so what we have is essentially Schwarzschild. And we assumed as well functional form for B of t. Okay, so essentially, when we plug in, when we assume a metric conductor is such, we have two scale factor, as I said, A of t and B of t, and then we will have another equation for chi. So at the end, what we have is three equation of motion, one for A, one for B, and one for chi, plus a constraint, the Friedman equation, essentially. Okay, so what we did here was to assume a functional form for B of t, such that everything close to the event horizon, it mimics a Schwarzschild solution. Okay, and that's what is what I show here. So I try to minimize the mathematical details. If you want to see more mathematical, you can either ask me or you check this paper. So graphically, what's happened, as I said, there are two scale factors. So A and then this B. Okay, this B is the one that is multiplying the two spheres, as I will show in a moment. Okay, so if we are in Schwarzschild, so essentially what happened is that we have here the singularity, this vertical line and this vertical line. So what happened is that this function B is 1 at the event horizon, okay, and then it goes to 0 when we reach the singularity. So the idea was the following. So we will take a function B, which behaves essentially like Schwarzschild here, okay? And it has a completely different value. In particular, it does not vanish here. It goes asymptotically to another value, okay? So that we avoid the singularity that we have here, okay? Now, here, the dashed line corresponds to h of b, which means essentially b dot divided by b. The red one would correspond to Schwarzschild. The blue and the pink one correspond to the numerical solution. Well, in this case, it's not numerical because it's a functional form that we assumed. And here, yes, it's the numerical solution. Okay, so here would be the, let me, exactly, here we will have the event horizon. Here would be the singularity for Schwarzschild. And in this case, what happened is that we don't have such a singularity. What would be the behavior of chi of t, of the 3-form? As you can imagine, close to the event horizon, the 3-form is 0. We are in vacuum, so we recover Schwarzschild. Now, as we move away, okay, from the event horizon, this one here, then the chi acquires some value, okay? The potential, what we have obtained numerically, it has to be negative, okay? And that will have some consequences, as I will mention in a moment, okay? So here it's 0 when we are at the event horizon. As soon as we move from the event horizon, okay, so it gets some values, okay? Negative. The behavior of these two scale factors, B and A, I remind you that A, in the case of Schwarzschild, is the red one. So, oops, sorry. B take the value 1 at the event horizon, where A, this one here is also taking the value 1. As we move away, okay, so A goes to infinity and it reaches the value infinity precisely at the singularity, okay? While here now, what happened is essentially this B does not go to 0. And because it does not go to 0, that singularity is precisely avoided. In a grammatical way, well, R is of course, is finite, okay? But as we know, for Schwarzschild, the Kretschmann scalar, this K, blows up, okay, at this finite value. While here, what happened is that it goes to a constant value. Now, how can we have this? So, because essentially, the null energy condition is not fulfilled, and this is what is shown here. So what happened is essentially this sigma which is nothing else but this contraction, it becomes negative. And if it becomes negative, so what we have is that the null energy condition is not fulfilled, which is indeed what happened in this kind of three-form model. That's why you have these extremely repulsive effects of gravity. Okay, if we look at the Penrose diagram, well, before going to the Penrose diagram, so as I said, this type of metric, they have two scale factors. This is the one that's played the role of A. Sorry, this A here is a constant. It's not the same A I put before. And this B is a constant, okay? So asymptotically, what we have is that the solution we got is an array space-time, okay? And those are the two scale factors. Essentially, what we have is a kind of the theta, b-dimensional the theta, times a sphere, okay? That's what we have. So the singularity that we had initially here, so it's sent to the future, so it's future infinity here, and it would take an infinite time to reach. Then, so what I want to stress here is that through a negative potential of the three form, we got an effective cosmological constant. That's not at all something easy. I don't know, and this I leave it as a question, I have no idea, if this we extend this study to, here we have a 4-dimensional space-time, so we need 3 more dimension, 7 dimension, if we'll get this piece here, which would be the theta in 4 dimension plus something n-dimensional. This, I don't know, I leave it there as a, I have no idea. Okay, now wormholes, and with this I finish. So essentially what we did was to assume a potential, which is quartic. These two coefficients, lambda and mu, are positive. Please notice that when this is written in terms of this chi, this three form, effectively it will appear a minus there, okay? Okay, so the three form degree of freedom is encoded on this chi. For the wormhole solution, we assume this type of static spherical symmetric metric. So when R, capital R, reach its minimum, so that would be essentially the mouth of the three form from where the flowing out condition has to be fulfilled. In order to analyze the system, it was convenient to introduce a dimensional representation, which is essentially this radial coordinate, to introduce this small x, this capital R, which essentially, as I said, the minimum would correspond to the mouth of the wormhole, is described by this capital X. Then we introduce a new capital lambda, although in this case, it's already the small lambda is dimensionless. It was essentially to include a new constant that measure the ratio between the small lambda and mu square. Okay, so this would be the capital lambda. Okay, so here I show the numerical solution. So for several values of lambda, or said in other way, for several values of this ratio of small lambda, this one over here, respect to mu square. So the mouth of the wormhole is when this variable x, capital X, or this capital X or large R, this one here, capital R, reach its minimum. So the mouth will be on the left-hand side, okay? So the minimum value of lambda. And what we see is that the larger is the value of lambda, which is as I move upward, essentially the larger is the mouth, the size of the mouth of the wormhole, okay? And here what we plot is essentially P of X, which is essentially this lapse function. And X is the dimensional coordinate related to the radial coordinate R, okay? Now, what happened with the three form, which is essentially this function psi, which is the other chi, simply written in dimensionless coordinates. So what happened is something very peculiar. So the larger is the value of lambda, which is the red one. Okay, the smaller is the value of Hello? Can you hear me?
Yes, yes.
Ah, sorry, I thought something. I'm finishing, okay? Just a couple of minutes and I'm done. Now, why do we have this wormhole solution? Because close to the throat, the null energy condition is not fulfilled, okay? That's why we have this null energy, this wormhole solution. Graphically, what is happening is the following. So this is a schematic way of drawing the wormhole. So this would be the mouth, okay, the minimum value of the radius. And so when we are here at the top, so essentially what happened is that the 3 forms 0, the potential is 0. So we have something that is asymptotically flat. Now, as we go down, we approach the mouth. So what happens is that the 3 forms goes down and then up. And it's on this gray part of the plot where the null energy condition is not fulfilled. So because of that repulsive effect, so we reach a minimum and we can, that's the mouth of the 3 form, okay? And why is this, I think this model could be important because they mimic black hole. What do I mean by the mimic? So if we look at the geodesic that would follow photons, okay, around the mouth, so it turns out that the values we obtain here for this one, so are essentially the same that those would be obtained for Schwarzschild black hole. And the same things happen if we look at the ISCO, okay? If the value of lambda is relatively large, so those values obtained for this wormhole solution mimics those of a black hole, okay? And with that, I conclude. So essentially, I described briefly a phenomenological approach to describe the late time acceleration of the universe through a constant equation of state. I explained how this could be done through 3 forms. And finally, and that was my main point, at least what I tried, is to convince you, well, if dark energy has some phantom nature, then that could be useful to get regular black hole and also to get wormholes that could be excellent mimickers of black holes. And thank you for your attention.
Okay, thank you. Thank you very much, Marianne, for your very nice talk. Is there any question or comment from the audience?
Not in the audience.
I have a question.
Mm-hmm.
Should I go ahead, Bebe?
Yeah. Ask.
Marianne, this is Ivan. Thank you for the talk. It was very clear. It's appreciated. I have several questions. One is that whether I mean, it's related to my previous question, whether the physics of this 3 form can be mimicked by something simpler. And, you know, I am thinking about dualities, right? You have a 3 form in 4 dimensions is dual to a 1 form. So whether the physics that you are describing can be exactly mimicked by, for instance, a 1 form field that we are more used to because of electrodynamics, and what would be the properties of such 1 form field?
Well, I know that some people have described the late time acceleration of the universe through vector field. So essentially, in this case, what they have to use is 3 vector field, which will be 3 1 forms, but those 3 vector field have to be orthogonal so that you can embed them easily in a Friedman Limit Robertson Walker.
But I am thinking just in a single one because of duality, right? We know that you know because of.
I mean, mathematically, yes, you can write. Where is the chat here now? I lost it. So yeah, mathematically, where is the chat here? So I can always do this epsilon ILK M, then times A sub the three last index. So I put I ALM, and that should give you essentially the same dynamics. So I mean, not the same dynamics. I can go from a 3 form to a 1 form.
Right, right. So my question is, why don't express everything in terms of 1 forms, which are are simpler and appear in other fields of physics? Or if anybody has tried to investigate that.
Well, I think because the equation of motion, they were simpler. Nelson Nunes and Tomiko Ivisto, they also saw how 3 forms can be mapped, for example, to K essence. But something, the mapping, when you want to inverse the equation, is not that simple.
Mm-hmm. Okay, thank you.
Welcome.
Oh, I have a question, Marianne. Concerning Weyl transformations, my question, Weyl transformations, local Weyl transformation or conformal transformation, is this the 3-form action, the massless 3-form action, Weyl invariant or not?
I don't know, but I would suspect no, because the trace is not 0.
Yeah, okay.
I suspect it's not, because the trace is not 0.
Okay, that is a signal of the breaking of this symmetry.
Yeah,
okay.
But I suspect, I have never done the calculation, but...
On the other hand,
yeah.
On the other hand, normally higher spin fields, when they are minimally coupled, are conformal invariant in 4 dimensions. That happens for electrodynamics, that happens for spin 1/2. So that happens. I wonder if
So just one, yeah. So unless they have some specific potential, the trace will not be 0. And therefore, I suspect they are not invariant under a conformal transformation. I suspect.
Yeah, if the trace is not 0, that is a signal that cannot be conformal invariant. Yeah, okay.
Now, yeah, that's what
it's fine. So you have answered the question. Sorry. Okay, any other question or comment?
So just for curiosity, the 3 potentials you have used to account for the accelerated expansion and for making black holes regular and for wormholes are different, right?
Yes. Yeah.
Are different from each other.
So let me go. So the one for the wormhole is this one. Okay. Which, when written in terms of the 3 form, that's why I said when we go from the representation on chi to the representation in A, we have to be careful because there is a minus sign that appears. So we have this shape on this case, but in terms of 3 form, the 2 coefficients are positive. Now, for the black hole, where did I draw it? Is here. Okay. So yes, it's different. I have it here, V as a function of chi, not as a function of A, but yeah, but the shape is would be the same, yeah.
And the way you picture this is that in different physical scenarios, the potential, should be different.
Yeah, they are not the same. And also, in relation to your question, if we go to dark energy, it's this one over here. This doesn't mean that if we use this potential, we don't have wormholes, okay? We use that one simply because numerically it was simpler. So the initial condition, let me go to the wormhole case, because here I avoided most of the calculation. essentially to impose the condition, what we did was to make an expansion on this small x, okay, around the minimum value of r, which would be the mouth of the wormhole. And that expansion was done in terms of, as I said, x squared, x fourth, and so forth, and a constant coefficient. And with this kind of potential, it was much simpler to carry the calculation. So if we assume the other kind of potential that we use for dark energy, maybe we have as well wormholes. For black holes, no. Once we impose that asymptotic form, that's the solution is close to Schwarzschild at the event horizon. So we fix the shape of the function b. We plug in this in the equation of motion, coming from Einstein equation plus the equation of motion of the 3 form, and we get automatically, let's say automatically, numerically, the potential.
So if one would like to solve all these problems, what would one
with
would
a
need?
single potential? Yes, you are right. Yeah.
Mhm.
Yeah, you are completely, yeah. But for example, for inflation, we have Starobinsky model, okay, R plus a constant R squared, but it's not the same potential that we use to describe dark energy.
Absolutely. Mhm. Thank you.
Welcome.
Okay, so Marianne, I think that it has been a very thank you. It has been a very nice talk for finishing this workshop. And well, as a last words, I would like to thank again to Gonzalo. It is not here, I think, and all the organizer for this wonderful workshop. And okay, so hope to see you next year in similar dates, and perhaps if the pandemic is smooth, we will see sooner. So thanks again for everybody.
Thank you.
Okay.
Thank you, and hopefully next time in Valencia.
Thanks.
No, me voy a dejar compartir.